Hey everybody, welcome to Algo Expert. In this video, we're going to be covering the question of the airport connections. This is an awesome question. It's very data structure and algorithm heavy, especially in graphs and graph traversal. And it's really the kind of question that I would encourage you to spend time working on. Spend time trying to solve this problem, trying to come up with a solution, trying to code it out, and then spend time watching and understanding this particular video. This is the kind of question that'll prepare you for a bunch of other problems, especially those that involve graphs and graph traversal. One caveat, though, is that this question is very, very difficult. It's in the extremely hard category here on Algo Expert, and that's really for two reasons. First of all, it's just a difficult question to solve. Okay, the algorithm and the sort of solution to this problem is very much non-trivial. But the second reason is that to actually code the solution out takes quite a bit of time, and it's a very lengthy solution, and it's a solution that you have to really put thought in to write cleanly. There's a lot of sort of design and structural work that comes into play when we're going to be coding out this solution or the solution to this problem. And that's why this question is so hard. It's the kind of question that would very likely not be expected to be solved in a 45-minute interview. I would say that in a 45-minute interview, a candidate would be more expected to just sort of discuss the question, maybe write some pseudocode or skip a lot of steps, probably get a lot of hints. It's a very difficult question, so don't be discouraged if you weren't able to solve it even in, let's say, 90 minutes, let alone 45 minutes. With that said, let's dive into the actual question. So the question gives you three inputs. The first one is a list of airports, and these airports are represented by strings, and more specifically by 3-character airport codes. And these are the kinds of airport codes that you see in real life, right? So in front of me, I've got a few of them, right? LGA stands for LaGuardia, JFK stands for John F. Kennedy Airport, and so on and so forth. So you've got this list of airports. One quick tangent that's important to note here is that when you're given lists of strings, usually you have to worry about the length of the strings in the list. Typically, you don't know the lengths, and so when you're dealing with time complexity analysis and space complexity analysis, you have to keep in mind that, your strings in your list might be of length n. Here, you know that all these airport codes are going to be of length 3, which is basically going to be constant time. So you can sort of put that in the back burner for now. Anyway, coming back to the inputs, you are given this list of airports, and then you're also given a list of routes. And the routes are lists themselves, or rather tuples, meaning lists of length 2, that represent a flight from one airport to another. Right? So you might have a route that says, EWR, HND, and that means that there exists a flight that goes from EWR to HND. Not necessarily back from HND to EWR, so it's a one-way flight, but that's the routes that we're given. And finally, the last input is just a starting airport, meaning what airport are we going to be starting at? And so then the question asks you, given these 3 inputs, write a function that is going to find the minimum number of new airport connections or new airport routes, right? New one-way flights that you would need to add in order to be able to reach every airport in the given list, starting at the starting airport. And the big note here is that we don't care about being able to go directly from the starting airport to all the other airports. We just want to be able to reach the other airports from the starting airport, meaning we're okay with layovers and stops and so on and so forth. So in the example that I've got in front of me, I've sort of jumped the gun a little bit. It's a spoiler alert here. And I've represented the 3 inputs that were given in a graph. or a sort of visual representation of a graph. And so here, like I just said, spoiler alert, this is going to be a graph problem. And this is going to be the kind of problem where you'd want to identify that it's a graph problem pretty quickly. And you'd want to do exactly what I did here of sort of drawing it out, because the structure of the inputs, right, a list of airports, a list of routes, and a starting airport doesn't really help you solve the problem at all. It's super hard to visualize. There's nothing much there. As soon as you put it in this sort of diagram that I've drawn here, right, then you can start to make sense of it. So here you can see I've got the starting airport, LGA, LaGuardia. Then I've got all the other airports sort of scattered about. And then a bunch of the airports have arrows pointing out from them. So like EWR to HND, ICN to JFK, JFK to LGA, and those are the routes, right? So you can imagine that for the EWR to HND, we probably had a route that looked something like EWR, HND, right? That meant that there's a one-way flight from EWR to HND. So we create a graph from the inputs, and of course, we're going to dive into the code walkthrough after to see exactly how we create this graph in code. Probably what we're going to do is just kind of iterate through all the airports, dump them in a hash table, and then maybe have all of the airports in the hash table map to their routes or to the airports that you can reach from them or something. Maybe we'll be using some kind of custom data structure. We'll think about that later. But this is going to be our graph building step. And now once we got the graph, we can kind of come up with the answer, right? In our case here, the minimum number of routes or of connections that we're going to want to add to be able to reach all the airports from LaGuardia is going to be 3, right? We're going to want to add one arrow from LaGuardia to EWR, one arrow from LaGuardia to TLV, and one arrow from LaGuardia to, and here this is where it gets interesting, either SFO or LHR or YW or SAN. And here you can sort of see that. For now, we'll just keep it at SFO, but you can sort of see that because if you go to SFO, you can go all around here. Right? If you go to SAN, you can go all around again. If you go to EYW, you can go to all of these again. Right? So SFO, SAN, this entire group here of 4 airports seems like it's sort of like identical. Okay, and this is obviously going to be really important as we dive more into the actual solution to this problem. But so the answer is going to be 3. Okay, 3 connections that you need to add minimum to be able to reach every airport from LGA. And again, for the others, hopefully it's clear, right? If you go to EWR, you can then go to HND, ICN, JFK. If you go to TLV, you can go to Del, DOE, SIN, CDG, BUD, and so on and so forth. Okay, so let's remove these arrows to give ourselves some space. How do we come up with this, right? How do we know that the answer is 3 algorithmically? Because this is the kind of question where here we were kind of able to see it because I sort of very prettily drew this graph. But of course, an algorithm doesn't see this. You have to tell it how to find this stuff. And of course, the more airports you have and the more routes you have, the more this problem becomes even impossible to solve by hand for a human being. So a sort of naive, immediate thought that you might have is that you could just find every airport that you cannot reach from LaGuardia, from LGA, from the starting airport. And for all of these airports, just add a connection, right? The problem with that is that you're going to have way too many connections. Because if you were to do that, then in our example here, there's actually not a single airport that you can reach from LaGuardia. Like, LaGuardia has no outbound flights in our example. So you would basically have to add 1, 2, 3, 4, and so on and so forth. I think there are like 16 or 17 other airports. You would have to add 17 or 16 connections if you were to naively just say, find all the airports that I cannot reach from LaGuardia, from the starting airport. And by the way that you would do that is probably by just, doing a sort of depth first search in the array or in the graph, starting at the starting airport and kind of toggling all the airports that you can reach as visitable or something like that, and grabbing the others as unvisited and unreachable. So, okay, this solution, while it kind of makes sense, it doesn't actually solve the problem. It gives us the wrong solution. Okay, so then how did we know that the three solutions were one arrow pointing to EWR, one arrow pointing to TLV, and one arrow pointing to these? Well, let's take EWR. The reason EWR was good is because EWR actually sort of unlocked a bunch of other airports. Like, maybe we could have gone to HND, right? And HND would have been great. We would have gotten one connection to HND, which also allowed a connection to JFK, also allowed a connection to ICN. But it would have been better to just say connect to EWR, because EWR can itself bring us to HND, whereas HND cannot bring us to EWR. So what this tells us is that every airport has sort of like a score. Every airport is like valuable, and some airports are more valuable than others. Like in this particular case, EWR is just objectively more valuable than HND, and certainly objectively more valuable than, let's say, JFK or ICN. In this example right here, right, like this sort of group on the left here, which sort of seems interconnected, we can sort of quickly tell at a glance that TLV is more important than all the others because it sort of connects to all the others. Like it connects to, I guess TLV connects to Dell. It only has one direct connection, whereas Dell has three direct connections, right? One to SYN, one to CDG, and one to DOE. But TLV connects to Dell, which then connects to the others. So even though Dell has three direct connections, TLV is still better than Dell, right? So I guess taking a step back, we said at first, like naively, we could have grabbed all of the airports, all of the unreachable airports, the ones that we know we can't reach from LGA, and just made connections to them. That was bad. The second sort of naive solution is to say, grab all the unreachable airports and see which ones have the most connections, right? The most immediate connections. But that would be incorrect because, again, like DL, right? Dell has, what am I circling? Dell has three connections, three direct connections. It has SYN, CDG, DOE. HND has two connections, ICN and JFK. And yet in both of those cases, TLV and EWR are more important, and they only have one direct connection. So the second sort of approach of saying find all the unreachable airports and grab the ones that have the most connections isn't actually like valid. So then what this leaves us with is we have to find why is it that TLV and EWR are so valuable. And the reason is because they actually unlock even more airports in the long run. Even though they might not be direct connections, they unlock the most airports in the long run, right? Or at least comparatively speaking. Like Dell only unlocks a total of 1, 2, 3, and BOOD by extension from CDG, so 4 airports, whereas TLV unlocks 1, 2, 3, 4, 5 airports on top of itself. So what we can do, because now we're starting to get an interesting sort of approach, is find all of the airports that are not reachable from the starting airport. We know that now. And in this case, it's literally going to be like all of the airports except for LaGuardia. And then give a score or sort of like a value score to all of these airports based on how many airports they unlock. Okay, so let's see what that gives us. Before we then like decide how to then visit all these airports, let's see what that looks like, right? So ICN, let's take a simple one. JFK. JFK is one unreachable airport. And how many other unreachable airports does it unlock? Well, we can sort of see that it doesn't unlock any, right? JFK basically only points to LaGuardia, and LaGuardia is not one of our airports that we care about. It's our starting airport. So we can assign a score of 0 to JFK. ICN, on the other hand, unlocks one airport, JFK, which is one of our important airports that's unreachable. So we'll assign it a score of 1. And remember, yes, JFK links back to LGA, but again, that's not an unreachable airport. LGA is not really important. So 1 and 0. HND unlocks 2 airports. 1, 2. Right? ICN and JFK. So we'll give it 2. EWR unlocks 1, 2, 3 airports. So we'll give it a score of 3. So already now we're starting to see, okay, clearly when we assign them these scores, we see sort of numerically that one airport is more valuable than the other. EWR is clearly more valuable than HND. We can continue on with the other airports, right? BOOD is going to be 0 because it doesn't have any outbound connections or outbound flights. CDG is going to be 1 and 2 because it goes to SIN and it goes to BOOD. So that's going to be 2. SIN is going to be just 1 because it only goes to CDG. DEL is going to be 1, which is DOE. 2 SIN, 3 CDG, 4 BUD. And then Tel Aviv is going to be, we can clearly see, 5, because it's going to be the 4 that DEL gives plus the DEL itself. All right, and then finally, let's go into here. So BGI gives 0, because it only points to LGA. So we'll put a 0 here. I'll go a bit quicker. ORD gives 1, DSM gives 2, and then SFO is going to give 1, 2, 3, right? DSM, ORD, and BGI, as well as 1, 2, 3, SAN, EYW, and LHR. So we'll give, so that's going to be 6, right? 6, and these are all going to be 6 because they all sort of loop back around between themselves, right? LHR gives 1, 2, 3, and then 1, 2, 3. EW gives 1, 2, 3, and then 1, 2, 3, and so on and so forth. Okay, so now we've got something. We've got all of these airports, and we know they're unreachable, and they have a score. Like, some of them are more valuable than others. So what if we start iterating through all these airports and saying, okay, start with the first one that's unreachable, that's got the most valuable score, meaning the most unreachable airports that it sort of unlocks. And let's add one connection to that. So let's start by saying, hey, let's grab SFO. SFO's got 6. 6 is the highest number here. I mean, there are 4 6s, but let's just grab one, SFO. We're going to add a connection to it. We'll add it in green. Boom. We added a connection to SFO. And now what do we do? So as a side note, I can write here on the side, boom, we've got one connection so far. Now what do we do? Well, we go to the second most valuable airport. That's going to be another airport with 6 as a score. So maybe like SAN. But do we add an arrow to SAN? No, because we've already actually counted SAN through SFO that unlocks it. So actually what we have to do is, when we're going down our list of unreachable airports, based on the ones that have the highest sort of score, or the highest number of unreachable connections, once we sort of create a connection to one of them, we should sort of eliminate all of the ones that it unlocked. So in this case, we would have to say, okay, remove this, remove this, remove this, remove this, remove this, remove this, right? Because SFO has essentially unlocked all of these, and we can skip them. We don't need them anymore, right? And this is really, really important. Now, then we can move on to the next one after 6. We've crossed out the first 3 6s, or actually the 4 6s, and now we go to 5. In 5, we've got TLV. So we're going to make a connection to TLV. It's going to be boom, like this. We can increase our 1 to be a 2. And now we're going to go traverse through TLV and all of its connections and remove them. Because again, we don't want, like, the next number here would be 4. And we don't want to count del, because del has been unlocked by TLV. So we're going to go through them and cross them out. And you can start to imagine that to do this, we're probably just going to be sort of like, maybe we'll be keeping track of all the unreachable connections from a given airport and iterating through them and removing them. Maybe we'll have some kind of like is reachable flag on each of the nodes. Here, by the way, I'm sort of giving a big hint that, again, this is going to be a difficult algorithm to code out. We're going to have to design a clear and unambiguous data structure and algorithm to make this code clean. But okay, so now we've got 2 connections. Now we get the next number that's the biggest, and it's 3, which is EWR. We can add an arrow to EWR. This 2 becomes a 3. And now we iterate through the EWR and all of its connections, remove them, or the unreachable connections, and now we're done. We don't have any more unreachable airports. And so, surprisingly, we've essentially solved the algorithm at this point, but we've gone through quite a lot of steps, right? To recap what we did, the first thing that we did, given the input, is we created a graph out of the input, right? We put everything in a graph, dumped everything in a graph, and we'll talk about exactly what kind of data structures and everything we use in the code. But we dumped everything in a graph that sort of looked like this. Then we grabbed all of the airports that were unreachable, and we did that probably using depth-first search, right? We sort of like traversed through all the airports, starting at the starting airport, using depth-first search, and all of the ones that we didn't visit, we just sort of said, okay, those are unreachable. Excuse me. Then for every unreachable airport, we iterated through them, and then iterated through all of their connections and all of their connections, probably again using depth-first search to assign them a score, right? Because when we went to TLV, for instance, and gave it a score of 5, we had to use depth-first search to say, okay, go through all of its connections, there's only del, then go through all of del's connections, sin, CDG, do, then go through all of these airports connections, so for CDG, sin, bud, for sin, CDG, and we had to probably mark things as visited to not double count them, and so on and so forth. And so, yeah, that was the second step, right? The second step was to sort of, the third step, once we got all of these unreachable nodes, or unreachable airports, actually traverse them and assign them a score based on how many unreachable airports you could reach by using depth-first search through them, right? And then finally, once we had that, we can sort all of these unreachable airports in sort of descending order, starting with the ones that have the most unreachable nodes that you can connect to, right? The highest value score. Create a connection to them. And for each one where you create a connection, iterate through all of its unreachable connections and mark them as actually reachable now. And this is our sort of green cross. And once we finish that process, we're left with, in this case, 3 connections that we had to add that enable us to visit every single airport. And that is the algorithm. Now, before we dive into the code walkthrough, which is going to be quite involved, like I said, in terms of space and time complexity, I do think that it's going to be far easier to understand the space and time complexity in the code. So we're going to focus most of our attention there. But we can sort of spitball it by saying, okay, we know that at one point we're sorting the unreachable airports based on the score that we've assigned to them. And in theory, we could have as many unreachable airports, or almost as many unreachable airports as we have airports. So we're probably going to have, A log A, where A is the length of the airports list, right? Or N log N, where N is the length of the list of airports. And then we know that we're doing a bunch of these depth-first searches to sort of grab all the unreachable nodes, then to assign all of the scores. So we're likely going to have a sort of depth-first search time and space complexity added on to that, which is going to be probably, the number of vertices in the graph as well as the number of edges. V plus E. You can look at depth-first search on AlgoExpert to understand how that time complexity works. But so yeah, we're probably going to be left with something like O of A plus R. I suppose I could write it out. It's probably going to be something like, let me erase this, time complexity equals O of A plus R plus A log of A, where A is the number of airports and R is the number of routes, right? A is the number of vertices in the graph. R is the number of routes or edges in the graph, but we'll see. We'll see in the code if we can sort of reason about it function by function, line by line. So with that, I hope that this conceptual overview made sense. Let's dive into the real meat of this problem, the coding walkthrough. All right, so we've got our airport connections function defined. It takes in a list of airports, a list of routes, and a starting airport. And we're going to start by outlining this primary method or this main method in the algorithm. So if we remember from the conceptual overview part of the video, the first thing that we did is we created a graph out of the airports and the routes. And that's exactly the first thing that we're going to do here. So we're going to declare an airport graph variable. And this airport graph is going to be created using a helper method that's going to be called something like create airport graph. And that's going to be a pretty simple one, probably the simplest method in our algorithm. This is going to take in our airports and our routes. And we'll get into the implementation of this method in a little bit. The second thing that we wanted to do when we went over the algorithm earlier is to gather all of the unreachable airports, right? We want to get all the unreachable airports from the starting point. And then for all of those, we want to sort of assign that score or that value, which essentially is equal to the number of unreachable airports that we can reach from these unreachable airports. Okay, so we'll start by saying unreachable airports, or actually let's call them airport nodes, because I think we're going to be using some sort of special data structure for our airports to store additional information like their connections and whether they're reachable and that kind of stuff. But so we'll say unreachable airport nodes is equal to get unreachable airport nodes. So we'll have another helper function that takes in our graph. And then what else do we think it's going to take? It's going to definitely take in our graph. Our graph should probably be able to sort of like contain the routes, right? The graph represents the routes, but we might still need the airports to iterate through, and then we'll definitely need the starting airport, which will be the thing that we start from. Then we will have our method that assigns that score that I just mentioned. So that it's going to be something like mark unreachable connections. Because like I said, the score is basically equal to the unreachable connections from all of these unreachable airports. And we'll probably mark them on whatever data structure we use to represent these airport nodes. And so this is probably going to be a method that doesn't return anything, that just does side effects. And I suppose it'll take the airport graph and the unreachable airport nodes. And we'll probably have to revisit this in a little bit when we get to it. And then the final thing that we'll do once we have all of these values, right, is we want to answer the question, which is to get all the minimum number of edges or connections that we need to add. So we'll say return get min number of new connections. And that's going to be our final method. And that, again, is going to take in, I guess, the airport graph, which we're going to be using for all of our methods, and these unreachable airport nodes that are going to have the unreachable connections marked on them. And we'll get into that in a second. Unreachable airport nodes. Okay, cool. So this is our main method, okay? So far, it's sort of structured following the logic of our solution that we covered in the conceptual overview, or that you might cover, on a whiteboard in an interview. And now we dive into the implementation detail of each of those. So the first one is going to be the create airport graph method. So this one would be a good candidate to ask your interviewers if you can skip, just because it might be, for the sake of this particular problem, not the most interesting to code out. But of course, for the video, we are going to go through it. So we're going to represent our airport graph as a Python dictionary or a JavaScript object. So we'll say airport graph is going to be a dictionary. This would basically be it's like a hash table, right? And we're going to store every key in this hash table as an actual airport name. So we'll say, for airport and airports, and we'll add on to the airport graph airport as a key. And the values that we want in this graph, at first, right, the first thing that I had given as an idea in the conceptual overview was to map every airport to its connections, right? So here it would be like a list of connections. However, we're actually going to need more info than that, right? We're probably going to want to know if an airport is reachable. We're probably going to want to know the unreachable connections that an airport has. And we're also going to want to know the actual connections that the airport has, not just unreachable connections. So there's likely going to be a lot of information that we want for any given airport. So that's why here I would very much recommend actually creating a new data structure that we're going to use to help us. We're going to call this data structure an airport node, and we'll implement it in a second. So airport node will probably pass in the airport, which we'll store on the data structure, but that's what's going to be stored on this airport graph. Okay. Now, this is the kind of thing that I was mentioning at the beginning of the video, of the conceptual overview. This is non-trivial, right? Coming up with this data structure in an interview, sort of preemptively before even diving into the rest of the nitty-gritty implementation details, is non-trivial, and this is why this question is really, really difficult. But so, let's see, what exactly will we want to store in this airport node? Well, let's define it, right? Airport node. When we initialize it, we just said that it's going to take in an airport, right? Which is going to be just the name. So I suppose we can store that just in case we ever need the name to access it off of the node. We might need this. But then the really important things are, we definitely want the connections, right? The connections are super important. And the connections are just going to be an array or a list. And here, right, we're going to fill up airport connections based on routes. And by the way, I'm using the word connections sort of synonymously with routes. I guess connections is just more specific to a single airport. Like an airport has connections. The routes are just describing a bunch of airport connections. But so that's going to be our connections. It's going to be an empty array at first, and then we're going to populate it up here on line 11. Then we're going to probably have a Boolean to know if an airport is reachable. So self is reachable. And this is going to be equal to, excuse me, probably we can initialize it to true. And then finally, we're going to have a list of unreachable connections. And this is going to make it much easier for us to count the number of unreachable connections and then mark them. Because remember, not only do we want to count the number of unreachable connections, which represent, again, unreachable connections means how many or what are the unreachable airports that we can reach from an airport, namely from an unreachable airport, from one of these unreachable airport nodes here. Okay, so kind of confusing, but we're going to want to keep track of those, not only to count them, but also at the end, if you remember in the conceptual overview, when we actually create a connection, we have to mark all of the unlocked airports as sort of done. We can skip them. That's going to be when this Boolean can come into play. Okay, and we'll probably use it also. I was talking about unreachable connections. That's where this unreachable connections is going to come into play. We're going to sort of iterate through them and say, okay, this is one of the unreachable connections that I just unlocked. So this is going to be an empty array, and we'll fill it up a bit later. Okay, cool. So now we go back to line 11. Let's delete it. So we've added to our graph all of the vertices, right? And now we want to add the connection. So we're going to iterate through the routes, right? For route in routes. We know that the first variable or the first value in our route, in a single route, which is like a tuple, is an airport. And the second value is also an airport, but it's the connection, right? So airport connection equal route. Again, here, just to clarify, this looks something like, LGA, JFK. So LGA is our airport, and JFK is our sort of connection that we can get to from LGA. So we've got airport connection equal route. And so here, we're going to add the connection to the airport's list of connections, right? So airport graph at index airport. We're now accessing an airport node, right, that we set up right here. Dot connections, dot append, because connections is a list, dot append connection. Okay? And then we go out of the for loop and we return the airport graph. Phew. So that is the create airport graph method. As sort of simple as it is, like I did mention that this is probably the simplest part of the algorithm to sort of code out. It's actually not that simple, right? There are things to take into account, and it's going to very much depend on the implementation detail or the implementation approach that you go with. I went with this airport node data structure. You don't necessarily have to go with that, right? If you don't go with that, you might not have the same sort of for loop here and the same logic here. Now, I figure that for this particular algorithm, it might be good to dive into the space-time analysis per method as we go through it while it's fresh in our minds. So that's what I'm going to do here. For this method, the create airport graph method, which is going to be line 2, right up here, the time complexity is going to be O of A plus R. This one is really simple. We can definitely calculate it. The others are going to be much trickier. O of A plus R time, where A is the number of airports and R is the number of routes, the length of the list of routes. And that's because we're iterating through every airport. So we're iterating through A airports and creating an airport node that's just sort of constant time, right? We're just setting a bunch of variables. And then we're iterating through R routes, and we're also just appending values. So that's sort of O of 1 time. Okay, so O of A plus R time, simple enough. And then it's going to be O of A plus R space, because we've got, why is it O of A plus R? Because we've got A airports, right, that we're storing. Here we've got constant space in all of these, but then we end up adding R connections, right? Appending R connections. So that's going to be roughly O of A plus R time, O of A plus R space. Okay, cool. So now we can go back up to line 3. We're at the next part, which is unreachable airport nodes. How are we going to get our unreachable airport nodes? Well, let's define this method. So get unreachable airport nodes. So this is going to take in an airport graph. It's going to take in our airports, and it's going to take in our starting airport. So why do we use these particular inputs? Well, to get the unreachable nodes, all that we're going to do, and I say this as if it's trivial, it's non-trivial, but all that we're going to do is depth first search through the graph, but starting at the starting airport, and then grabbing all of the airports that we haven't visited. So we're going to keep track of the ones that we were able to visit using depth first search, and grab all the ones that we haven't visited, add them to a list of unreachable airports, and maybe also set their Boolean flag is reachable to false. Okay, so what is this going to look like? Well, we're going to have to keep track of the visited airports, or the airports that we can visit using depth first search. So that'll be just a hash table. Visited airports is going to be equal to just a dictionary in Python, and we'll set airports to true or false. Then we're going to call a helper method, which is going to be our depth first traverse airports, and this is going to be the depth first search algorithm portion of this method, and that's going to take in our graph. Of course, can't really do depth first search without a graph. It's going to take in our starting airport, because we're going to start by doing depth first search at the starting airport, and it's going to take in our visited airports, and we'll get into this helper method in a second. But once we've got now a bunch of visited airports here, you can imagine that we might have like LGA true, right? And maybe we'll have like, I don't know if we'll keep track of the ones that aren't visited. We'll probably just keep track of the ones that are visited here. But so now, once we've got this, then we can say, okay, our unreachable airport nodes is going to be just an empty array, right? And let me give myself a little bit more space so that we can prefer when the code is higher up. Okay, so unreachable airport nodes is going to be an empty array. Now we can iterate through all the airports, right? For airport in airports, what are we going to want to do? Well, we're going to say, if the airport is in visited airports, we visited it through depth first search starting at the starting airport, then it's not unreachable, right? So then we can just skip it. So if airport in visited airports, continue, skip it, right? Otherwise, well, we want to not only mark it as unreachable, but we also want to add it to our unreachable airport nodes. So we'll probably grab the airport node by saying airport node equal airport graph at index airport, I guess, or at the key airport. And then airport node dot is reachable equals false, right? This means that if the airport was not in the visited airports after we did our depth first traverse, then it's not reachable. And unreachable connection, or no, not unreachable connections, unreachable airport nodes dot append the airport node. And again, like the reason that we want airport nodes as opposed to airports is because we're going to need to be able to access all these values, like the scores and the unreachable connections and all that. We want to be able to access these very easily, so we don't want to have only airport names here. Okay, and so once we're done with this, once we're done iterating through all the airports here on line 22, and doing all this, gathering all the ones that are unreachable and marking them as such, we can just return the unreachable airport nodes. All right, so that's this method. Now, before we move on to the marking all the unreachable connections, we do have to define this depth first traverse airports. So we'll do depth first traverse airports. So what is this going to take? Well, this is going to be just really simple DFS, depth first search, right? So it's going to take a graph. It's going to take our airport, which started out as the starting airport, and it's going to take in, I guess, visited airports, right? And standard DFS, if we've already visited a node, we skip it. So if airport in visited airports return, right? If this is a recursive function, which it is. And by the way, here, I am sort of speeding through this because this is an extremely hard question, like I said. So we're really assuming here that you are familiar with depth first search and with graph traversal. If you aren't, please do check out a lot of our other graph questions on the website on AlgoExpert, namely depth first search, and maybe even like breadth first search and these other kinds of methods that might be helpful here. And so once we've checked that the airport is in visited airports, then we want to actually visit it and mark it as such. So we're going to say visited airports at key airport is equal to true. And then we want to do the same thing through all the connections of that airport, right? Because like, what does depth first search entail? It says, and by the way, we don't even need to do that depth first search here. You could, like I just mentioned, use breadth first search or some other graph traversal method. Depth first search is just very easy. But so here, what you want to say is like, for every connection in whatever airport we're visiting, visit that connection, right? And then visit that connection's connections and see all of the airports that we can sort of eventually reach having started at the starting airport. So here we can say connections equal airport graph at index airport dot connections. And then we can say for connection in connections, depth first traverse airports, the airport graph, the connection, and the visited airports. Okay? So this is sort of simple depth first search. Check if it's visited. If the thing we're at is already visited, return. Otherwise, mark it as visited in our visited airports, which started out as an empty dictionary here, an empty hash table. And then grab the connections, and for each of those connections, recursively call depth first traverse, passing in the connections and, of course, the visited airports. So what is the time complexity and space complexity going to be for this method? Right, we're taking the method on line 3 here, get unreachable airports. Well, we've got this whole depth first traverse airports method. So that's definitely going to be standard depth first search time complexity, which is O of A plus R, number of vertices plus the number of edges, which are the routes, right? Because we're going through all the airports, right? Like we're definitely going to be like we are going to be visiting at most all the airports and at most all of the routes, right? If that makes sense. Wait, let's see. Does that make sense? We start at the starting airport and then we go through the connections. Yeah, at most we're gonna be visiting all the vertices in the graph and all of their edges is the idea. So again, by the way, this is where like the time complexity gets very shaky in this algorithm and gets very complicated. Like, would not be expected to get a perfect time or space complexity analysis here. So it's really more about just showing that you can sort of reason about it and maybe making a sort of educated guess. There's definitely some like amortized analyses that we can do here, but just not worth it. So we're going to do O of A plus R time. And I guess here we're also then iterating through all of the airports here afterwards. But here we're just doing constant time checks. So that's going to be, O of A plus R plus A. So 2A, you can drop the 2 time. And then for space complexity, I guess it's just going to be O of A. Because depth first search is going to have some recursive implications for the space complexity. And then and that's just going to be, what is that going to be? That's just going to be like the potential like depth of the tree, or the graph, which would be A, total number of airports. And then here you're iterating through all the airports. So O of A space. All right. Okay. So we're getting somewhere, right? We've created our airport graph. We've gotten all of the unreachable airport nodes. Now we want to actually say, okay, well, how many nodes do you unlock for me, right? How many nodes do you unlock for me? So mark unreachable connections. I think this is going to be like the trickiest function to write maybe, and especially the trickiest from a time complexity point of view. So mark unreachable functions or unreachable connections. What is this going to take? We said it would take an airport graph and unreachable airports. So airport graph and unreachable airport nodes, I guess. And let's see. Here, we want to say, for every unreachable airport that we have, figure out how many unreachable connections we have. Right? So for airport node, in unreachable airport nodes, figure out how many unreachable airports we can connect to. So let's grab our airport. Airport is going to be equal to airport node.airport. By the way, this is where it comes in handy that we stored the name of the airport on the airport node. Declare number of unreachable connections to be an empty list. And now do another depth first search, but slightly different than this, like slightly different logic, but still the same like depth first approach technique, depth first search approach technique, to add all the unreachable connections. So depth first add unreachable connections. And here we're going to grab in our airport graph. You always need a graph when you're doing depth first search. Grab in our current airport, which is the current airport that we're at. And it's an unreachable airport. And pass in the unreachable connections. And then I guess if we're doing depth first search or some kind of depth first search method, we're going to need a visited set of airports. So we'll use an empty dictionary here. And then, of course, once we've got these unreachable connections, this is just going to be like a side effect, right? And it's going to alter this array here. You could probably also have this be just return a list, but I'm just going to do it this way. And then here, we would just set on the airport node, right, the unreachable connections to be unreachable connections. This is why, again, it was really nice that we did this data structure airport node here that has unreachable connections. That way we can sort of like assign it here, and we'll use it elsewhere. Okay, so now we need to define this. So depth first add unreachable connections. So this method, what does it take? It takes in our airport graph, as always, it takes in our airport, it takes in unreachable connections, and this, we said the fourth argument is, again, visited airports, because, as always, when you are dealing with depth first search, you need to know if we're dealing with a visited airport. So that's going to be one check. If airport is in visited airports, then return. By the way, to clarify, like, we want to know the number of unreachable airports for every, or number of unreachable connections, right? For every unreachable airport. So we need to do depth first search on all of these unreachable airports, and we need to do a new depth first search on all of these, which is why for every single one of them, we need to have this visited hash table, right? This new visited hash table that's reset in every step of this for loop. Okay, if airport is in visited airports, return. The first check, actually, that we're probably going to want to do is if airport graph is reachable, like if we're dealing with an airport that's reachable, then return. Right? We're only caring about an airport here that is unreachable, right? That's the only way that we care about this. So once we do that, we can visit the airport. We can say visited airports, airport equal true. And we can say unreachable connections dot append airport. So I suppose that here we're going to start by essentially appending ourselves to our unreachable connections, which is fine, because that means that basically every unreachable airport is going to have one extra unreachable connection itself. That shouldn't really matter much for the logic of our algorithm. Like our algorithm will still work. Okay, cool. So we append whatever airport we're at to the unreachable connections, and then we say, all right, let's just do this depth first search again. So it's going to be similar to here where we grab the connections and call the method for every connection. So we'll say connections equals airport graph, at index airport dot connections, just to simplify things, right? So we don't have to write this again. For connection in connections. And here we do a call to this, right? We add the unreachable connections, passing in the airport graph, passing in connection, passing in unreachable connections, and the visited airports. Whew, okay, so very tricky method that is sort of similar to the previous one, but a little bit different. Again, like I said, like this is a great algorithm to really test your understanding of graph traversal and depth first search. Like by the end of this algorithm, depth first search should become very, very sort of second nature to you. Like understanding, okay, I have to mark nodes as visited, then I have to iterate through all of their like edges, which in this case are the connections. In terms of time and space complexity, this is one that's going to be really complicated because this, right, depth first search typically takes like we said, the like v plus e time, where v is the number of vertices and e is the number of edges. But here we're only dealing with unreachable connections, or we're dealing with connections, but only of unreachable airports. So, like, in theory, it could be at most v plus e, but it might be less. And then we're doing this for every single airport in the unreachable airport nodes. Again, in theory, there could be almost a unreachable airport. So maybe it's like O of a times a plus r time. But that seems a little rough. This is where, you would have to just sort of explain to your interviewer the logic. I'm probably going to go with O of a times a plus r time complexity here. Again, because like we're iterating through almost a airports, and then for all of these, we're doing, up to a plus r time complexity in the depth first search. So this actually kind of complicates our algorithm. It's not quite what I said in the conceptual overview earlier. I think I'd forgotten this multiplication here. And then the space complexity, I believe, is just going to be O of a space, because we're just adding, up to a like unreachable connections, and we're going to have a bit of space complexity complications from the recursive algorithm of this. But again, here, like I really want to emphasize that for a question like this, that's this difficult, where like the space-time complexity is this convoluted, this is not really what you're going to be tested on in the interview. It's going to be much more like, can you just reason about it and give like a ballpark estimate? Okay, so we are almost at the end. We're at this final method, get min number of new connections. So now, to reiterate, we've gotten the airport graph. We've gotten all the unreachable airports from the starting airport. We've marked all of the unreachable connections that are reachable from the unreachable airports. If that isn't a sort of mind mess for in order not to curse, then I don't know what is. So now we are going to do that final method. And just to make sure here, we don't want to return anything because this is a side effect method. So, final method. Let's do this. We defined get min number of new connections, and this is going to take in our airport graph as well as our unreachable airport nodes. So the first thing that we want to do here is we want to sort these unreachable airport nodes by their score. What is their score? It's the number of unreachable connections that they have. That's the number of airports that they sort of unlock. Okay, so this is where, again, our data structure, the airport node, comes in really handy, because we can do all this logic because of that data structure without having to do like extra iterations through lists and keeping track of maybe extra data structures and stuff. We have it all in these airport nodes. So we can say unreachable airport nodes dot sort, right? We're going to sort them. So in Python, we can use sort of a key, which is going to be like our sorting function. So we'll use a lambda function or an arrow function. So lambda airport, for every airport, what we're going to care about is the length of that airport dot unreachable connections. And then one more thing that we need to do is we need to sort these. So we're sorting them right now by the number of the length of unreachable connections that they have. But then we also want to reverse that sorting, right? Or that order. We want to sort them in descending order, meaning We want the one with the biggest number of unreachable connections to be at the beginning. So we'll do reverse equals true. Okay? And now we can finally start keeping track of our number of new connections. So we're going to say number of new connections equals 0. This is going to be the thing that, our final answer. Let me give myself a bit of space. Yeah, like this. For airport node in unreachable airport nodes. If airport node is reachable, continue. Why would an airport node that's contained in unreachable airport nodes ever be reachable? Because remember, sometimes we're going to be getting unreachable connections from a given unreachable airport and mark them as hey, we've handled these now. We've unlocked them. Remember, SFO unlocks a bunch of other airports. So it's possible that we're still going to have an airport in unreachable airport nodes that is reachable now. Okay? So if it's reachable, just skip it. Otherwise, of course, increment our number of new connections. And then for connection, this is the important part, for connection in airport node dot unreachable connections, airport graph at key connection dot is reachable equals true. Right? So we can sort of close the loop on everything by saying, hey, when we're traversing these unreachable nodes, if we're at an airport that isn't reachable, and we're going in sorted order, descending, starting with the ones that have the most unlockable, unreachable connections, and add a connection to our answer, minimum connection, and then say for every connection that we have in the unreachable connections from this airport, mark them as reachable. They're done. We don't need to visit them anymore. So when we get back to them on line 63, we can skip them in line 64. Finally here, we are going to return the number of new connections. All right, and so how is this going to work? This is going to be O of A log A, right? Because we're sorting up to roughly A airports, unreachable airports. You can imagine that all the airports might be unreachable except for the main one, which was in our example, right? LGA was the only one that was reachable. The starting airport, sorry. And then, so A log A plus, we're iterating through all the airports in unreachable nodes, so that's probably going to be up to A, plus we're iterating through all of the unreachable connections of the airport. So the unreachable connections would be, at most, this is going to be R, right? Because remember, at the beginning, we're given R routes. So, there only are possible unreachable connections, so to speak. Right? Yes, in total, across all the airports, there only are unreachable connections or are routes. So there can only be, at most, are connections and therefore are unreachable connections. So we're going to go with this for the time. And the space, I think, is just going to be O of one space because we're sorting in space. Here, we're just overwriting values, and we're not using any recursion, so this is all constant space. We're not storing any extra stuff. Okay, so airport graph, get all the unreachable airports, mark all of their connections that are unreachable, and grab them, right? And then sort them by how many unreachable connections they have, reverse that so that it's in descending order, go through all of them, starting with the ones that are the best ones that have the most, unreachable connections. Skip them if they're already reachable. Increment this value. Mark all their unreachable connections as reachable. And voila, we're done. So in terms of the total space and time complexity, that is literally the last thing we have to do here. I believe it's going to be, so let's see. It's going to be O of A plus R from here. O of A plus R here, we can sort of drop that. A times A plus R, so plus A times A plus R. So I guess this becomes A plus R times a plus 1, right? If my math is correct. So a plus r times a plus 1, which I guess probably we can remove this. I guess we can just keep it as a times a plus r plus a plus r plus a log a, which was below at the bottom here. And then this a plus r here, I guess that would be like 2a plus r, but we can drop the 2. So it's going to be something like this. Again, like this is really a rough estimate at this point, for whatever it's worth. At least it shows that you are able to sort of analyze this problem. And then the space complexity, I think, is going to be O of a plus r space, I want to say. We had a plus r, a, that dropped the a dropped the a, 1, yeah. So it's going to be a plus r. It's like 3a plus r, but you can drop the 3. Okay, so that is it for this algorithm. I really hope that this was helpful. This was probably the longest algorithm, at least longest coding walkthrough that we had to explain. Hopefully this really made graph traversal a lot clearer. Hopefully this gave you a lot of inspiration for like how to make your code clean, how to structure it, how to make use of some of these data structures, some of these creative data structures. And that's that. I hope this video was helpful. I'll see you in the next one.